Good morning and most welcome to 1417. I would today read an article by Chris Fields, Boundaryless World, and it's also part of a book written together with Deepak Chopra, 2014, Brain, Mind and Cosmos. And I can ask my dear colleague Kalle to have a little introduction on the author himself, Chris Fields. There you go.
Hello. So Christopher Fields, he has two addresses. He is partially in France, in Caen-Minervois, which is a small medieval town in the Aude department in Occitanie region in southern France. He is also in the United States, in Mesilla, NM, what will it be? NM, okay, it's Mesilla NM in the United States. Anyhow, so he has a PhD in philosophy, and he has an MA in molecular and cellular and developmental biology from University of Colorado in 1988. He has been very active in the last years, publishing department. He has been a scientific director at the National Center for Genome Resources, Santa Fe, from 94 to 96, but he has also very most recently, what is his most recent scientific consultant, and he has also PhD studies, postdoctoral associates. So he has published more than 200 papers, over 200 referred publications. Nuclear physics, information physics, biophysics, cognitive science, information systems, neuroscience, molecular development biology. And this publication is from 2014 with Deepak Chopra as editor. So I give it back to you, Hans.
Well, Chris Fields seemed to be quite a prolific writer. I prepared a little looking at his YouTube clips. Is very prevalent in YouTube as well, being interviewed and having discussions. There is one discussion which caught my interest. He has with Carl Friston, that we mentioned many times before, Carl Friston. So seems interesting, and I will start to read out of the article now. This boundaryless world. It's a little ingress here. Separate individuals with separate identities through a shared linear time is the heart of classical physics that quantum theory rejects. And there are many gems in this ingress already. Last lecture was about separate identities and separate individuals, and I also mentioned last lecture that implies linear time, or what we usually call the washing line of linear time. A sort of time Newton invented in order for things not to happen all at once. Ask yourself, can you determine by observing the world around you exactly which parts or aspects of the world are causing your current, right now experience? Can you determine exactly which parts or aspects of the world caused any of your past experiences? It may take some reflection, but common sense will tell you that the answer to both of these questions is no. Past experiences are, after all, in the past. What we observe now can tell us what might have caused a past experience, or what probably caused it. But only time travel could give us access to what actually did cause it. Is it enough, however, to make the past present? Does even right now experience reveal its causes? Can you demonstrate that your current experience is being caused by the print on this page, and only by the print on this page? Can you prove to yourself that your experience is not being caused some other way by some other means? Very good, I would say, my comment. This is bringing David Hume a step further. Eloquent questions.
Han står exakt som Billy i Lego Billy. Så hänger det samman så.
The question of whether the causes of experiences can be uniquely determined has traditionally been left to philosophers. or to fantasy writers like the authors of The Matrix.
Ja. Hade du aldrig klädd? Fan. Ja, det är han Tunkan. Johan. Ja, Johan. Det var oss. Då tog du upp första versionen, sen så var det denna. Ja, när man började
In everyday life, we assume that we know what is causing our experiences. If we see and hear someone speaking to us, for example, we assume that someone is really there and is really speaking. And that their being there and speaking is what is causing our experience. Going about our daily business would be impossible without this assumption. Science clearly assumes this too. Explaining the events that occur around us, the job of science, is largely a matter of explaining what caused them. The events we find most intriguing or most troubling are the ones for which we can find no satisfactory cause. This chapter explores the consequences of questioning our everyday assumption that we know what the causes of our experiences are. It begins by examining the consequences of a second deep assumption. The assumption that while how we describe the world to us, it does not matter to the world.
Jag kan inte sänka musiken.
Okej.
Det styrs inte härifrån, det styrs från en annan, så jag kan inte påverka musiken tyvärr. Ja, tyvärr, ja, jag förstår.
This is an essential assumption of science. It is the assumption that there is a world out there that is independent of our human thought patterns and languages. My comment there, this is of course Thomas Nagel's The View from Nowhere, or A World at Large. While this is merely a practical working assumption for most sciences, it is built into the very heart of quantum theory. The most accurate theory of the physical world that we have ever had. When combined with the assumption that we humans are finite observers, however, this deep assumption has a surprising consequence. It implies that we do not and cannot know the causes of our experiences precisely. It implies that we cannot know that two experiences have the same cause. Hence, we can never say, on the basis of experience, that we have encountered the same individual thing on two separate occasions. This insight allows us to understand, without having to do any mathematics, some strange predictions of quantum theory.
Ja, jag har lite vatten med också. Ja. Det gör jag. Så här hela halsen. Och så här burken. Det är viktigt.
It also allows us to understand why our brains devote so much energy to the task of making up connections between our memories and our present experiences.
Ibland har jag gjort det. Nu släpper det helt enkelt. Men vi bokar en varje som du inte längre. Jag betalar ju pannan. Så jobbigt att få det i...
Understanding this in turn allows us to recognize time and individual identity for what they are.
Ja. För det är lördag.
Feelings we have about our experiences, feelings that help them make sense. But that hide their true character as unbounded, unpredictable processes.
Jag har köpt något roligt i alla fall.
Embracing these unbounded and unpredictable processes leaves us with a sense of greater empathy, both for ourselves and for the world.
Kolla, kanske har några kläder. Nej, kolla andra så de har några kläder.
An old and deep assumption. Next chapter.
Han blir lång då.
What would the world be like if how we described it affected how it worked? It is perfectly ordinary to believe something rather like this, that how we describe the world affects how we work. How we act on and respond to the world. Naming a disease, for example, can dramatically change how we behave. That is why we value medical diagnosis. What would the world be like, though, if naming a disease changed how the deceased behaved? This would be a strange world indeed. One of the most basic assumptions of the sciences is that there is a way that the world works. Whether we can figure it out or not, our names for things, our ways of describing things, and our theories of how things work are important to us. But according to this basic assumption, they have no effect on the structure of the world or on how it works. Human languages and theories are just that, languages and theories. The world goes about its business completely independently of such things. Turning this assumption into scientific principle requires making it more precise. One way to make it more precise relies on the notion of decomposing the world into a collection of named or even just noticed things that are of interest for some purpose and on which attention is focused, together with everything else on which attention is not focused. Think, for example, of driving to work. One's attention is focused on a few things. The road, other cars, one's destination, perhaps the day's anticipated events. most of the rest of the world remains unnoticed, unnamed, undifferentiated from the general background of the world. Such decompositions of everything or the universe into one or a small number of things, the systems of interest on which attention is focused together with a shared environment comprising everything else, is not just commonplace but essential in science. My commentary is Chris Fields is referring to the landscape or the canvas, and we already discussed earlier everything, how problematic that is. One cannot measure everything that is going on, or from a broader perspective, any more than a tiny fraction of what is going on. So the environment that remains uncharacterized in any investigation is huge. With this notion of decomposing the world into what is interesting for the present purposes and what is not, the basic assumption that there is a way the world works can be stated more precisely. How the world works is independent of our choices of decompositions. It is perhaps more forceful to state it as a symmetry principle that science must respect. All of the ways of decomposing the world that we do, can, or could employ are equivalent in at least one way. None of them affects how the world works. As we shall see, this principle of decompositional equivalence has some surprising consequences. Before examining these, however, let us look at some of the ways this principle is used by the sciences and particular by physics. The basic idea behind physics, even in the ancient world, is that there are laws of nature that apply in all situations across the board. In the European Renaissance, when this kind of thinking could get you burned at the stake, the laws of nature became God's laws. Under that rubric, they still applied across the board and still could be figured out if one were clever enough. Laws that apply across the board are laws that do not depend on our names and descriptions. In a world in which the laws of physics were applied in practice mainly to planets and cannonballs, this subtle symmetry did not have much of an impact. However, as physics became more mathematical and experimental methods improved, this began to change. Newton's mathematical formula applied to all things that had mass and were capable of motion. They said nothing about size or shape. Theorists quickly apply them to abstract entities, and experimentalists equipped with new methods tested the results. A classical understanding of fluid flow, for example, employs such an abstraction. One can imagine a volume element or voxel of fluid embedded in the overall flow but enclosed within an imaginary boundary that prevents that exchange of material with the surroundings but allows the exchange of energy or momentum. Deformations in the shape of this voxel correspond to changes in the pattern of the flow. These can be visualized and modeled with equations that predict measurable changes in pressure or flow velocity, no one would imagine, however, that drawing such a voxel boundary would change the physics of the flow. Indeed, such imagined voxels are useful precisely because they can be drawn anywhere. Classical fluid dynamics, in other words, relies on and hence requires the assumption of decompositional equivalence. Decompositional equivalence lets us draw the voxel boundary anywhere without changing the physics of the flow. I think I had to repeat. Decompositional equivalence lets us draw the voxel boundary anywhere without changing the physics of the flow. So you see, you can construct the abstractions in that fashion you prefer for your desired goal or what you would like to do. Where you draw the line is something you decide. It's caused by your intentions, what you prefer. And this is especially clear in this depiction, as you can find in the paper, figure 1. Maybe we could put it in here, in my little summary here. And as you see from this simple depiction is, you decide yourself what sort of abstraction to use and where to draw the boundaries. And I really like this example because I encountered it myself when studying to be an engineer. And if you are given the example like this on a plate, you don't realize that already a border has been drawn and a sort of abstraction is already present. What I assumed was that was a natural flow, and our equations, our calculations covered everything of that flow. But it doesn't. Actually, it is absolutely random boundary drawn up for certain practical purposes. And these very helpful boundaries are not out there. They do not partake into what is nature. Nature, you could say, give potentialities for the boundaries and the borders you draw. But the amount of borders are absolutely infinite. And the different divisions, like the velocity of the flow, the area of the flow, the force of the flow, are all different ways of making boundaries, human-made boundaries, for a specific particular purpose. And as Chris Fields writes, in a specific situation. You want to achieve something, and I think his example with the cannonball is especially pertinent. There are two reasons for this. I really like the cannonball. One is that it absolutely revolutionized artillery, battery movement. It had an incredible impact. The armies, generals that adopted the cannonball projectile equation, they won victories. Battles were made, and even new borders, speaking about borders, were drawn thanks to the use of the cannonball projectile equation. But remember, we are talking about cannon, gunpowder, a cannonball, a specific purpose in a specific event. And what we do, we think we can sort of generalize this to all events, that we can take it out of context, and we can move it everywhere we want. The idea of the projectile has been used in understanding light, something that was vivid and vital until the Morrison-Morley experiment of 1887. The second take is that we quickly forget that we were dealing with a cannonball or a waterfall. And we sort of think that it is the equations, it is the theory that we apply to something. But it is the opposite happening, as Chris Fields points out. We start with the waterfall or the cannonball, and then we assume the theories from them. And we forget in which order things happened. We sort of forget the two-handed, where we did the things, where they had an effect. I think it's obvious from this rather sharp comment of Chris Fields. They are bound not to work when put out of their specific circumstances. And we forget the timing completely. And this is maybe the worst aspect or most dangerous aspect. The Newtonian world is a timeless world, so it sort of forgets that you need to catch the moment. A general would never apply cannons after the battle, neither would he do it before the battle. It has to be done in a very specific, precise moment. And this is something the Newtonian paradigm doesn't care about at all. All moments are equal, just as space is completely equal and homogeneous. And all moments are identical. Like an impossible necklace where all the pearls are exactly the same, made from an oyster coming from the planet Putnam or John Searle planet, in an otherworldly way, made identical. I challenge you to find those identical pearls somewhere in the universe. Well, even more, what would it mean to be exactly the same as a pearl if you're not inhabiting the same position in space? Even that is a difference. Maybe a comment from my dear colleague Kalle here.
Okay, thank you. Since you were speaking about cannonballs and cannon, I would like to mention a homonym, canon with one N, canon, that is like a literary canon. Literary canon, the word canon in this with one N, canon, it comes from measuring rod in ancient Greek. And in Hebrew you have also a similar word canon, which means reed, that is the things that grew in the Nile. And measuring rod is interesting, canon as a measuring rod, because you think that canons, like canons of literary works, are permanent, but they can change. For instance, I'm now reading this course, Apocryphal Gospels. We think that, say, the New Testament is fixed canon, 27 books, but books can sometimes go out and in, like Martin Luther, he didn't like the book of James, so it had a ambiguous position, and then some didn't like the book of Revelation, and they had ambiguous position. And the Gospel of Nicodemus is canonic in the Ethiopian church, so different Christians have different canons with one N. And so this is everything depends on the observer. If you have an Ethiopian observer, he will perhaps like the Gospel of Nicodemus, where you have also Pontius Pilate as a saint. We don't see Pontius Pilate as a saint, but Ethiopians do. So we think always everything you have always a mixed measuring rod, like a neutral, fixed for all, but it's always depending on the observer, whatever. If you have a literary canon or whatever, like a canon with two ends, you shooting something, and you need an observer to shoot well, and you need also an enemy, unfortunately, and so forth and so forth. So I give back this to Hans.
Yes, that's a strange coincidence. You mentioned Ethiopian church, and I was just about to mention, well, almost Ethiopians, Nubians. Why is that? Well, I wanted to give an example here on how we, even before the event of these developments in technology, in thinking, that even predated Newton, say. There were tendencies of this already going on in the late Middle Ages. We had a stream of thought that for some, I can't get my head on it, but for some reason did not early on even not like the idea of observer-dependent reality. That we had a choice, the situation meant something, and for what purpose. And that is an example coming from The Conquest of Abundance by Paul Feyerabend. He there mentions the Greek philosopher Xenophon, and Xenophon makes an objection to the variability of gods. Sorry. Especially when you think of the different depictions of God Xenophonus noted. You know, the Greek people were a seafaring people. Socrates compared the Greeks to frogs around a pond. The pond was the Mediterranean, the Red Sea, the Black Sea, and the Greeks were everywhere. That made for an excellent opportunity to compare. Small deviations in how statues of gods were made, like the ones of Zeus, Athena, and so forth. And he said, isn't it odd that the gods of the Illyrians are fair-skinned, tall, and red-headed, just as the Illyrians themselves. And how come the gods of the Egyptians are straight-haired, short in stature, and with bright shining brown eyes, just like the Egyptians? The last example he gave was the Ethiopians or the Nubians close by. They had thrub-nosed, dark gods with curly hair. The conclusion that Xenophonus made is very, very Newtonian. He saw the observer as a fault on the gods, something that made the gods less. Although he didn't do the trouble of defining what these subjective tendencies actually were made of. He just assumed this must be something amiss here, and that the gods therefore could not have unique iconoclastic properties. They could no longer be iconic. So his God, and I think he even tried to diminish plurality and make it just one personality lacking God that didn't obey space and time like it were deficits of reality. And this is so close to the Newtonian later development. So I would say for me, I can also see this as a thinking mistake. It's a bit sloppy of Xenophanes. He doesn't go into the details of exactly the movement that exists. He didn't see how the different movements were among these peoples. It is like he saw them at a distance only, or by hearsay. Paul Feyerabend called this mistake, or rather clumsiness in observation, for monetizing. When you do a lot of business and you use money, which was almost by this time a new commodity, your ways of doing business get speeded up, less careful, less in the world, and more into what you want to perform. And I can imagine in the end you lose the why somewhere. Just like we lost our why when it came to the canon. Why do we have the canon? What do we want to do with it? Implies a specific moment, specific place, and a specific purpose. All is forgotten almost, in a sort of amnesia. And the canon in the end is just a phantom. Could we maybe have a pause there? And I continue here after the little summary, and it's the first paragraph on page 5 in the article. The revival of the ancient Greek notion of atoms during the European Enlightenment further enhanced the centrality of decompositional equivalence within physics. And decompositional equivalence, my remark, is the way of cutting up the world, so to speak, and generalize from that cut up and sort of forget what you did afterwards. Atoms had mass, and things made of atoms clearly could move. Newton's laws therefore apply to atoms. Suddenly one could wonder, is the motion of an object not just the collective motion of its constituent atoms? Might the behaviors of planets and cannonballs be mathematical consequences, whether calculable in practice or not, of Newton's laws applied to their atoms? The new sciences of thermodynamics and chemistry seem to confirm this. What the atoms in a thing were doing determined what the thing was doing. My comment here, can you see the tautology inherent in this take? Could it be the case that the universe is just a bunch of atoms going about their business, and that everything we see, including ourselves, is just a description of this business from our idiosyncratic human perspective? Could it be the case that the universe is just a bunch of atoms going about their business, and that everything we see, including ourselves, is just a description of this business from our idiosyncratic human perspective? Were this the case, decompositional equivalence would imply that our human perspective is not just idiosyncratic, but one of many that are equally valid. That what we regard as ordinary reality is merely one of arbitrarily many ways of parsing the world. This idea that absurd phenomena might be just surface features of an underlying invisible dynamics, what philosophers would call epiphenomenalism, provided a third option in metaphysics, challenging both the naive realist acceptance of ordinary objects at face value and the idealistic rejection of the perceived world as an essentially illusory construction of the mind. It never reached a dominant status in philosophical circles, but it motivated scientists to ask whether Newton's laws were in fact obeyed by atoms. Well, that is a reversal that Chris Phil is pointing out. The quantum revolution. Everyone now knows, of course, that Newton's laws are not obeyed by atoms. Phenomena at the atomic scale, the subatomic scale below it, and even the molecular scale above it are governed by the laws of quantum theory. The revolutionary new physics of Bohr, Einstein, Heisenberg, and Schrödinger. In the world of quantum theory, electrons are both waves and particles. Cats are both dead and alive, and only probabilities can be predicted. The world of quantum theory is, moreover, our world. How true is my comment on that? The theory's predictions are regularly confirmed to accuracies of better than 1 part in 10 billion. Cell phones, digital cameras and computers, to say nothing of nuclear weapons and power plants, all testify to the predictive success of quantum theory. All incorporate quantum technologies that depend on the violation of Newton's laws. Without the quantum revolution, the technological revolution of the 20th century would not have happened. What, however, is quantum theory? Textbooks present it as a morass of arcane mathematics. Both Bohr and Richard Feynman famously opined that anyone who was not bewildered by it did not understand it. The four basic principles of quantum theory can, however, be stated without recourse to complex mathematics. Two of these principles, as we will see, are consequences of the assumption of decompositional equivalence. Understanding quantum theory requires understanding what is meant by the physical state of a system. The primary concern of physics is to explain and, if possible, to predict changes in this state, and the main difference between classical physics and quantum theory is in how they describe it. Suppose the system of interest is a chair. Classical physics describes the chair's physical state with two numbers. One representing its position in some coordinate system, its GPS coordinates, for example. Well, you can choose the coordinate system of Descartes also. And another representing its momentum. Momentum is a classical concept combining an object's speed, its direction of motion, and its mass. Momentum is a measure of how much force an object can transfer to anything it collides with. Viewing the chair as a collection of atoms does not change the structure of this description. A position and a momentum are written down for each atom in the chair. The position of the chair is then the average position of its atoms, and the momentum of the chair is the sum of the momenta of its atoms. Once more we have the cannonball presiding. One can add additional numbers representing other degrees of freedom to the state description of the chair, for example, specifying its electrical charge or the speed with which it is rotating, its temperature, the color it's painted, or any other observable property. One could also add these additional numbers to the state descriptions of its atoms. The list including all the numbers needed for the predictive task at hand is regarded as a complete description of the chair for the purposes of classical physics. The construction of such a classical description of a physical state relies on an implicit assumption that one can measure the position, momentum, electric charge, angular momentum, and any other physical properties of the chair that one wishes to write down. This implicit assumption in turn relies on two even deeper assumptions. One is that the chair can be identified independently of its position, momentum, etc. This is obviously required. If one cannot find the chair, one cannot measure its position. The other is that the properties to be measured can be measured independently. This is also obviously required if measuring the position changed the momentum, for example, and measuring the momentum changed the position, one could never measure both and hence never write down a classical state description. Do remember this. This is of incredible and great pertinence to everything. If measuring the position changed the momentum, for example, and measuring the momentum changed the position, one could never measure both and hence never write down a classical state description. I think that deserves a glass of water.
Här kan vi prata om synkronicitet.
So after a rather unexpected meeting here at Café Tintin in Gothenburg, I will try to compose myself and continue where I left off. The development of quantum theory was motivated by many experiments. But one of the most basic motivations is that the second assumption required for the construction of classical state descriptions is violated at atomic scales. Measuring the position of an electron, for example, does change its momentum. And measuring its momentum does change its position. This is the content of Heisenberg's famous uncertainty principle. It is easy to say why this might be so. Electrons are small and measuring devices are big. Think of trying to measure the position of one of your hairs by having someone carefully approach it with a car. What Heisenberg's principle points out is that any measurement requires physical interaction, and any interaction that yields an answer in finite time involves an exchange of energy between the measurement device and the thing being measured. In the quantum world, such energy exchange is significant. Some pairs of measurements can be made in a way that the inevitable energy transfer does not pose a problem, but many cannot. Position and momentum in particular cannot be measured independently, so classical state descriptions are impossible. Quantum state descriptions have a peculiar form that is dictated by the non-independence of measurements and the phenomenon of wave-particle duality. Instead of expressing the state of a system using just the last observed value of whatever properties are being measured, quantum theoretic state descriptions incorporate a representation of what the system could be doing during the period when it's not being observed. Why this is necessary is easiest to see by considering the phenomenon physicists call spin, which is responsible for, among other things, the effectiveness of Polaroid sunglasses. Measuring the spin or filtering the polarization of light in the vertical or up direction will create a beam of up polarized light. filtering the up-polarized light in the horizontal direction at a right angle to the vertical will yield no light at all.
Ja.
Ja, liksom lite så här, liksom jobba precis under mig nästan. Alltså liksom, det känns som att man får...
If, however, a filter oriented at an angle between vertical and horizontal is placed between the vertical and horizontal filters, some light will get through. Look at figure 2. How could this be? The explanation is that the intermediate filter selects light with an intermediate polarization. One that incorporates some vertical and some horizontal light. Quantum theory makes this notion of some of the measurable alternatives being incorporated into a quantum state mathematically precise, and incorporates it into all quantum state descriptions.
Hej. Så, currypasta. Varsågod. Här längs, eller runt hörnet har ni bestick och kryddor och sånt.
A quantum state describes, in other words, what is physically possible, and does so in a way that allows, given a mathematical specification of what will be measured, the calculation of what outcomes are probable. Given this concept of quantum state, the basic assumption of quantum theory can be stated as follows. Quantum states are descriptions of physical possibilities from which probabilities of observational outcomes can be calculated. Interactions between quantum states can be described mathematically as sums of interactions between their components. Measurements of quantum states yield sets of real numbers, one for each independently measurable physical property. The quantum state of a composite system can be expressed mathematically as a product of the quantum states of its components. That's it. From these assumptions, the mathematics of quantum theory follows. The physics of quantum theory is another matter. It is even more up for grabs now than it was when Bohr and Einstein had a famous debate at the 1927 Solvay conference. Physical interpretations of the above assumptions range from the hyper-pragmatic shut up and calculate attitude of most academic physics classes to Henry Stabb's mind-matter dualism. Christopher Fox's notion that quantum theory is not physics at all, but rather part of probability theory, the infinitely branching parallel worlds of Max Tegmark or David Boas, or at least a half a dozen other options. This question of physical interpretation can be set aside, however, in order to ask a simpler question. What does quantum theory tell us about observation? As we will see, what it tells us is that our earlier question about the causes of our experience is not merely metaphysical. Heraclitus' revenge. The Greek philosopher Heraclitus, 500 BCE, is famous for saying, "You cannot step into the same river twice," and for generally believing that our notion of identity over time, including our concept of our own identity over time, is deeply flawed. The empirical successor quantum theory demonstrates that Heraclitus was right. To see this, let us examine the second and fourth assumptions of quantum theory more closely.
Först fick jag syn på det där. Det irriterade mig det. Och sen kom jag ut och kan knappt betala. Jo, betala kunde jag ju, men det var ju så krångligt med det där. Jag skulle blixtra där. Det betalar jag aldrig. Det är lite mycket. En blixtra. Då ska man ju bara dra kortet. Det skulle jag stå där och slå
We will see that they are both statements of decompositional equivalence that have, in the context of the rest of quantum theory, some interesting consequences.
Har du inte själv om det där jävla skiten? Du vet inte själv om det där? Nej, det är du inte.
The second assumption of quantum theory is that interactions between components of a pair of quantum systems can be added together to calculate the interaction between the systems. Can put a pause and make a you can clearly see here is how Chris fields are slowly pushing us towards the realization that in the quantum world we cannot make predictions exact in the old formula. The coordinate system, the GPS location, and the momentum cannot simultaneously be decided.
Se alltid till att få tillräckligt med kontanter. Och det är inte det jag har. Jag är mitt själv, jag betalar alltid kontanter. Jag har alltid gjort det. Men så här på en anledning hade jag inte det idag. Men jag hade det ändå när jag lyckades skrota upp det. Jag har aldrig sett ett system som och då har jag ändå betalat jättemycket. Du förr betalade jag i alla fall, men nu betalar jag alltid lite.
This is a very, very well spread illusion that is of a sort of exactness of classical physics that simply does not exist.
Vi säger att det kostar 600 kronor. Mat och allt det där.
The first tendency is of course the unquestioned idea of what. Stephen Rosen would call a subject in front of object in space. That is the coordinate system which remains unquestioned in the idea of an exactness stemming from it. And we have earlier mentioned what Lee Smolin and Roberto Unger revealed as being a fault in our thinking, that by assuming initial conditions we will get the classical laws, but from the classical laws we can induce the initial conditions. So you could say that this co-equal and co-dependent establishing locks things into the fantasy of exactness of the world. This is what Chris Fields showed with the vortex. In order to calculate it, we must make a boundary. We discern momentum from location. This arbitrary division, unquestioned and fundamental, brings its force upon us and makes the idea of the classical physics prevalent and strong. You could even call this a sort of double bind. Or why not call it an entanglement that is unobserved, unquestioned, or unknowledgeable in the darkness. It's a sort of lockdown, and Chris Fields, I think the simplicity of the drawing makes it even more compelling. It's absolutely brilliant in its simplicity. And I also think it's, for my own take, very interesting. I have experienced and encountered the wave many times in my education as an engineer, and it seems so correct that the spin boundaries made is left out of the presentation by default, and not even the instructors or teachers when I grew up were aware that there was a boundary some way and somehow established long before it was even decided.
Tack så mycket! Jag tänkte hon sa fisk, det har vi fortfarande, det är roligt.
Nej, men jag pannbiff med det, sa jag ju. Ja. Och tvillingar.
So we are presented with a already established fact,
Den är
and
underbar.
everything
Ja,
which
det
I
är
was
tonsägen som var här.
was already decided for
Det var
me,
väl bra.
and the one presenting it weren't even aware of it.
Kalle skulle jag ha.
Vad vill du ha?
Kalle.
Ja, det var det.
I think this shared unobservance or unawareness, maybe it's more proper word, is what often is called priming. We are already lured or sucked into pre-established order.
Hon kommer ut med det sen.
And we are nothing much and nothing much more than fishes in
Ja, det är bra
water.
att maten är varm.
It is impossible to be aware of the medium we were already cast in.
Kommer de med det här? Sen.
Det har de
It took quantum mechanics to make that possible.
och då får jag köttbullar till.
Ja,
And I think that is why this discovery, this conference 1927 in Solvay in Brussels was so utterly important,
Ja, varsågod.
tack så hemskt.
because that was the first time it was revealed properly to the public that
Kommer inte på middags.
unproposed, unhypothesized perceptions were ruling what conclusions or theories we could construct. And that all the theories that we had constructed previously were governed by these establishment or lockdowns. I think borders are precise words.
Ja, det är Jeanette. Jag sitter och äter. Förfärligt.
Lite starkt. Tintin.
Ja, ja, jag har fått det gott här. Ja då. Ja. Hej, hej. Vad Maria frågar vad jag fick gå om tvn.
Vadå?
Maria frågar vad jag fått gå om tvn.
Ja, fick du det?
Min tv.
Mm. Du har fått igång den.
Jag har fått det gott.
Det var kväll då.
We need to know
Men det var
that the
bra.
borders exist
Det var duktig då.
because otherwise we will not be able to move them to put a measurement situation in its
Så jag vet
proper
när jag är hemma.
context. We will not be able to get all the knowledge we need.
Hon ringde sen när jag var hemma.
And that's why I think the cannonball that's been used for all things from photons to electrons to throwing of masses and the projectile trajectory of any matter object has had such an important influence. But it is forgetfulness that it comes from a certain specific situation that makes the possibilities much less becomes possible. Chris Fields is with his borderless or boundaryless world, proposing not a world without boundaries or borders, but an understanding that borders themselves are part of knowledge. Once we understand that, we will also be able to consciously move them.
Det är bättre när du får allting i ordning. Va? Det kan du också göra.
And I think consciousness is getting diminished when we don't see the borders. Something is constantly blocked out of vision. Our predictive power becomes less. Our possibilities becomes locked down in bodily tension. And the reason for that is our experience very, very seldom fits the cannonball. If ever could happen, that is extremely rare. But once we got that into the understanding to see that what borders something, and mobile phone is maybe not the best example because it has a natural border. I think it's still arbitrary. Maybe we need to have this constellation, or we can cut the mobile in half or 2/3 to better fit the situation. When we do our battles with our cannonballs, or maybe we don't even need trajectories and momentum in that way. A boundaryless world is not free of boundary, but there are boundaries that are true to the purpose, more fitting, more accurate. As Chris Field said, it is 10 billions much more accurate than classical physics ever could be, already at the outset, from the, so to speak, theoretical basis. I think I end there and I say thank you very much. Have a very nice afternoon, which it is now. Bye bye for now. This is the lovely coffee shop Ting Ting. Here he goes to the moon. Bye bye Ting.